Have you ever just watched a top athlete and thought, how could I describe what they're doing with, perfect precision? Not just saying, wow, they're fast, but how fast and in what way exactly? Well, today we're unlocking the physicist's toolkit to do just that. All right, let's get into it. I mean, we all get what it means for something to move, right? But how do we actually capture that movement with the language of science? What's the real difference between just seeing motion and being able to truly describe it? That's the big question we're going to tackle today. And to make all these ideas really come to life, we're going to follow the explosive journey of a world-class sprinter. We'll be with them from the crack of the starting pistol all the way to the finish line and even a little bit beyond. Their story is going to be our guide. So at its absolute core, it's this simple. Motion is just a change in position. Picture our sprinter, coiled and ready in the starting blocks. The second that gun fires and they explode down the track, their location is changing, moment by moment. But as you're about to see, that simple idea is just the starting point for a much richer story. And they're off. Okay, so to really start telling the story of this race, we have to get clear on two ways of measuring their path. They sound super similar, I know, but in physics, the difference between distance and displacement, well, it's everything. So let's break this down. On the left, you've got distance. Think of this as the total ground you covered, every single step. It's like the reading on your car's odometer. It just goes up and up. Now on the right, you have displacement. This is totally different. It's the direct as the crow flies path from your start point to your end point. It doesn't care about the winding journey. It only cares about where you ended up relative to where you started. Now for our sprinter's race, which is a perfect straight line, the numbers happen to be the same, 100 meters. But did you catch that extra word for displacement? Forward. That direction is absolutely critical. And this simple case is a great way to show why we need two different words, because in the real world, things almost never move in a perfect straight line. Okay, so let's really put this to the test. Imagine our sprinter crosses the finish line and then immediately turns around and jogs 50 meters back towards the start. So how far have their feet actually traveled? 100 meters out, 50 meters back. That's a total of 150 meters. That's their distance. But what about their displacement? Well, they're now only 50 meters from where they originally started, right? So their displacement is just 50 meters. See? A massive difference. So we figured out the sprinter's path. But the question everyone wants to know in a race is, how fast did they go? To answer that, we need the next tool in our toolkit, calculating their average speed. Let's see how this works. So the first piece of our puzzle is the total distance they traveled. And for this race, we know that's a nice clean 100 meters. And because our sprinter is an absolute champion, they covered that distance in a blistering 10 seconds flat. And that's the second piece of our puzzle. Now, the formula that connects these two is beautifully simple. Average speed is just the total distance you've gone divided by the total time it took you to get there. It's that easy. All we have to do is plug in our numbers. So, what do we get? We take 100 meters, we divide it by 10 seconds, and boom, we get an incredible average speed of 10 meters per second. That's how we put a number on their amazing performance. But hey, the story doesn't stop at the finish line. Our sprinter is flying at top speed, and now they've got to slow down. And that very act of changing their speed brings us to our final, super important concept, acceleration. Now, when you hear the word acceleration, you probably think of hitting the gas in a car, right? Speeding up. But in physics, acceleration is any change in velocity. So yeah, speeding up is acceleration. But, and this is key, slowing down is also a form of acceleration. And here's the real kicker. Even just changing your direction while keeping the same speed is also considered acceleration. Let's just visualize our sprinter right after they cross that finish line. At that moment, they're at their peak speed of 10 meters per second. 1 second later, they've eased off to 5 meters per second. And then a second after that, they've coasted to a complete stop. That steady drop in speed from 10 down to 0 over 2 seconds, that is their acceleration. In this case, it's a negative acceleration. All right, we've followed our sprinter all the way from the starting blocks to a dead stop. So let's pull back for a second and put together our complete toolkit for describing motion. This table just lays it all out so perfectly. But look really closely at that last column. See how displacement and acceleration are called vectors? That is such a powerful idea. It means that for those two concepts, the direction you're going is just as important as the number. It's not just how much things changed, it's which way they changed.
And that is really the most important thing to take away from all this. These four ideas, they're the actual language of motion. It doesn't matter if you're talking about a sprinter, a planet orbiting the sun, or a car turning a corner, you are always using these fundamental building blocks. So I'm going to leave you with a little puzzle to chew on. If a race car is zooming around a circular track and its speedometer is locked in at a perfect 100 miles an hour, is it accelerating? Now remember what we said about changing direction. The answer is a fantastic example of how these rules work in really cool ways, and it might just surprise you. Thanks for joining me, and as always, stay curious.